Good morning, friends. Today is, what day is today? May 20th. May 20th, 2025, and it's time to go through these slides again. As an exercise, this is something I do frequently. I have several slide decks, and I encourage others to find them and use them also, so that when you watch this, you might be a teacher thinking, hey, I could grab these slides, but would I say the same thing as this dude, this guy who made them? Maybe not, but you could have your own narrative, but the slides would be the same, kind of like a textbook. You don't always have to say the same thing as I do, and I don't say the same thing as I go from one rendering to a next. I change my banter. As you've seen, if you want to go back and look at other examples, search on something like dimension and synergetics or slides. So I've added some slides this time. Didn't take this picture myself, didn't make it to the 67 World's Fair. I did go to the 64 World's Fair in Seattle, but I was really little. I was probably 8 years old. Or was that in 62? So maybe I was even younger than that. But I've been aware of this, and this has been an important um, icon, you could say, in the Fuller corpus and really in world history. And this is especially interesting picture because it shows the USSR pavilion in the foreground, even a little piece of the corner of the building, and then that's the Buggy's giant thing in the background. You could say that was USAID. I mean, in a way, it was propaganda. But so that's what pavilions are at World's Fairs. You're showcasing your nation's technology. It wasn't actually USAID. It hadn't been invented. I think it was he worked with USIS, though, I believe. It was originally going to be a different implementation, more focused on his fuller projection, the map. But it turned out to do that. They did this instead, and it worked. It worked great. It had a little train going through it, so it's kind of proto Epcot. This is how Fuller's technology looks today. I would say he had zero to do with this one, but his thinking is in the lower Earth, and the engineering now includes that we can build these things. So this is like a dew line radar protector, except this is just a weather station much further south. It's not on the dew line. The dew line, the Defense Early Warning System. See, Fuller was very involved in all this Cold War stuff. He was actually involved in the hot war stuff too. He's got a career that goes all the way back to World War One, actually. And his classmates at Harvard, a lot of them perished in World War One. So he had a long life, and it was all involved in defense contracts, a lot of it, right? So here's a little bit of his books by and about, like the two green covered ones. Those are from a collection of his work, both writings and pictures, that was for a museum exhibit, I believe in Germany, and maybe traveled some. Lots of books, lots of literature. So if you're getting into this stuff newly as a teacher, don't worry about running out of material. And do come at it kind of as Pound Era poetics. In other words, it's literature, it's meant to be read as literature, and it has a lot of math in it. And we look at the math here. And we dive deep into that math. It's not like we are trying to skirt the math, but we don't want this to fall into the hands of purely literalists, people who try to read it as a literal particle physics or something. There's been too many of those. So keep it metaphoric and find those passages that tell you that that's how you should keep it. I'm just not making this up, all right? So that makes it seem incomprehensible because, James Joyce, right? Pound era literature is not always easy to read. Finnegan's Wake. It's easier to read than Finnegan's Wake, I would say. But it is mostly prose, right? And yet it embeds a lot of math. And so here's some of that math. And so here's a cube that couldn't possibly have a whole number volume in our way of thinking because the edges are second root of 2. Now you can divide through by 2 and have that diagonal, face diagonal, be 1 if you prefer. This will relate to balls that we'll look at in a second, like when packing balls together. But you'll agree with me whether that edge is second root of 2 or second root of 2 over 2. The way we normally would get the cube's volume is just raise that number to the third power. Height times width times breadth. Height, width, breadth. And we're saying they're all the same here, second root of 2. So the final volume of this cube is second root of 2 to the third power. And so a third of that, which would be the volume of the inscribed tetrahedron, couldn't be rational. Couldn't. 1/3 of second root of 2 to the third power is not a rational number. And yet, in synergetics, that is what we want to have. We want to have a unit edge, unit volume tetrahedron. And you could say, well, that's not unit edge. Well, it could be if you're talking in terms of one diameter, one sphere diameter or 2 sphere radii. It could be either. You see the tetrahedron on the far right. 4 balls packed together. The center to center edges are either 2 radii or 1 diameter, so 1 or 2. So that's the tetrahedron we're talking about. So you can picture putting balls at 4 of the 8 corners here that touch each other at the mid edges, right? So 4 balls make a tetrahedron. There's the tetrahedron. It has the same edge length as the diameter of one of our balls, and it has unit volume. And how do we do that? How can this have a volume of 1? It says at the bottom, 1/3 of second root of 2 to the third power is certainly not equal to 1. So that is a tension we set up. We say Bucky's off on the wrong track. He'll never be able to make this work. And then we unveil the solution here. How it's done is we don't create cubic structures or rectilinear structures when we multiply 3 numbers together. We go by a 60-60-60 degree angle instead of a 90-90-90 one. So 5 times 5 times 5 is a tetrahedron of 125, but 125 unit tetrahedra. And there's a 2-dimensional analog to this where we use unit triangles. A guy named Wayne Phillips had that down in Australia. Came to that independently, the Utragon guy. So here's Fuller's prose, and it's not that easy to read at first. It's a language, but basically he's taking the tetrahedron and using it to change. In his namespace, he's going to talk differently about what dimension means and what third powering looks like. Like there's a lot of revectoring, as I call it. There's a lot of changing in meanings here, which is why the whole talk is quote unquote dimension and synergetics. Like how does he change the meaning? And he goes with 4D as his sort of marketing label. And that's a big meme in the whole of the 1900s, right? But people use it in different ways. That's what you have to absorb, is that although people say math is the universal language, actually it divides up into many namespaces, and it's not like every author is using the same terms the same way necessarily. So once we do have unit volume tetrahedron with edges 1 sphere diameter, then we have these other relationships, ratios, that they're there in the XYZ world as well. XYZ meaning the normal way to compute volume, and normal, I use that word advisedly. So we have this whole very accessible to like middle schoolers, even preschoolers, like Montessori. This is like a different approach to volumes once we've made the switch, and our unit volume is now a unit edge tetrahedron, which also is involved in the sphere packing lattice called a CCP. So there's an integration of polyhedra with thinking in terms of lattices. Well-known math, not saying Fuller invented it all, but he did make the shift to the unit volume tetrahedron, which then subdivides into subtetrahedra we could call A modules, as he does. Then there's the octahedron, which you need a B module as well as an A module, but they have the same volume, 1/24th left and right versions. We have the plane nets, and we've had sixth graders fold up these plane nets and make, one tetrahedron per classroom because we need 24 of them. Some folded left, some folded right, inside out of each other. Lots of concepts that you need to start getting early, like chirality or handedness, or, there's other words for it. You know how much time we spend talking about congruence in these early grades, often neglecting that isomers or inside outs are considered congruent, whereas that difference in chemistry can be huge. Or in Tetris, a left and a right piece, you can't just flip it inside out necessarily in reality. So then we have this whole namespace of mites. They're space-filling tetrahedra. This is known to other mathematicians as well. It's just they don't use the same vocabulary. Our coupler of 8 mites turns out to be another space-filling unit volume. Again, those who are into Archimedean duals and packing thereof, they know these things, but they don't have as integrated a vocabulary in my view. So then we have these T and E modules. So there's what we call the beast modules. You can add a K for a K module, but BEAST, these are just tetrahedral partitions, shapes, wedges, building blocks, particles, he calls them. So we've got a small vocabulary of those, and the T and the E modules, for example, both have the same shape, and they both build the rhombic tricontahedron, as you can see here. The technique with the modules is to take a face, like a triangular face or a square face or a rhombic face, and go crisscross and break it up into 4 triangles. Or in the case of a triangle, when you go with A modules, going back here, we see the A modules, we get 6 of them per facet, right? On each quadrant of the tetrahedron, we have 6 A modules. That's why 6 times 4 equals 24. 3 left-handed, 3 right-handed, and then we build the mites with that. The T and the E modules, we start having these interesting relationships in terms of volume and so forth. Once you make that change, that innovation, and have your tetrahedron play the role of unit volume instead of the cube, and yet with unit edges in a sphere packing lattice, then there's a lot of low-hanging fruit, a lot of interesting other volumes you're going to want to pick up on, such as the rhombic tricontahedron of volume 7.5 tetravolumes, which is going to share vertices with the rhombic dodecahedron of volume 6. Phi gets into the game. The RT made of E modules and the RT made of T modules, slightly different volume. One of them encases a unit radius sphere. The other one has volume 5 exactly. And the difference between the two is very, very small. And that's something Fuller makes a big deal out of it in volume 2 of Synergetics. Talks a lot about the T and the E module. But he doesn't use phi, and so one thing that David Koski and I have done is say, what's the harm in bringing phi back as a quantity, second root of 5 plus 1 all over 2. And once you do that, you can streamline a lot of the expressions that Synergetics already contains. You can shortcut, make them easier to read and stuff like that. The S module is another one. It's long been known that you can inscribe an icosahedron and an octahedron, but we have set sizes going, so we have a set volume for this S module because that octahedron is the volume 4 octahedron, the one we talk about back in this slide, volume 4 octahedron. The red one and the orange one together complementary fill space. The volume 6 also fills space all by itself, and the two go together. In other words, the rhombic dodecahedron will encase each ball in the CCP packing much as we see the rhombic tricontahedron encasing a ball here. The RDs do that, the rhombic dodecahedra, and fill space at the same time. Something Kepler knew about. Now we can, interestingly, find all these identities which David Koski has found. For example, just to take a simple one, the S module, phi up, meaning we scale up all edges by phi, meaning the volume goes up as multiplied by phi to the third power. So when we multiply all the edges of the S module by phi, its volume goes up by phi to the third power. So we call that S3, meaning S module with phi up one step. We can go up again. We can multiply all those edges by phi, and it goes up by another phi to the third, so phi to the sixth. So the S3 plus S6, and this S3 is not to be confused with the synergetics constant, which we also call S3. Those two together equal 1. In other words, you see the top identity here, tetrahedron, and the far right, 1s6 plus 1s3. So two S modules, one scaled up by phi, and the other scaled up by phi, and then scaled up by phi again. S6, add those together, and you get precisely the volume of the tetrahedron. So a bunch of identities using S and E module, and then how do we get the volume of these guys? Base times height. The usual way is not going to work, with the constant. Well, with a constant, yes, it works, but we have to figure out how to natively get the volumes of any tetrahedron, not just any regular tetrahedron. If the regular tetrahedron has edges A, then its volume is A to the third power. But we want all 6 edges to vary independently. And so we have A through F, and that's what this formula does. On a computer, it's lightning fast. It's very similar to something Euler came up with, but also Piero della Francesca back in the 1400s came up with this. And so in the source code these days, we can swap in any of 3 different algorithms for computing any of these tetrahedra, S module, A module, B module, based on its edges alone. Feed it the 6 edges, and out comes both the tetravolume and we'll call it the IVM volume, or the synergetics volume. Well, those are the same. Tetravolume and IVM volume are the same. XYZ volume, the old volume, like we learn normally in school, that would be yet another volume. So IVM versus XYZ volumes. And on the right here, we see the IVM volumes of our nested polyhedra in what we call the concentric hierarchy. The E modules, phi up, phi down. In other words, you can shrink them by phi as well as expand them by phi. Jitterbug transformation, well established in the synergetics literature. It's a long discussion. You can buy commercial copies. It's in math books. And it shows why the cuboctahedral number sequence and the icosahedral number sequence are the same sequence. Check out Online Encyclopedia of Integer Sequences, for example, and put in the numbers 112, 42, 92, 162. You see here on the right, it's not that easy to see this, but it's taking a ball packing, just an empty hollow shell, of balls packed in a cube-octahedral conformation, which is the CCP, and through jitterbug distortion, a series of steps, E, F, G, by the time we get to G, we're looking at icosahedral symmetry. Same number of balls, but changed. Because it's hollow, we can do this. Hollow shell. At the bottom, you see, more of a straight line view of the same transformation. There's the cumulative number of spheres in each layer of the CCP. So you start with this nuclear sphere and you come outwards, 12, 42, 92, 162, like that. So the little blue around each one of these ping pong balls, the little blue polyhedron wireframe, that's the rhombic dodecahedron I was talking about, of volume 6 in our canonical hierarchy, our way of packing. Here's another view of the ball packing we're talking about, called the CCP in the literature, independently of anything Bucky gave us. But he called it the IVM, isotropic vector matrix, because he's focusing on the skeleton of rods that interconnect all sphere centers, which then gives you tetrahedra, volume 1, and octahedra, volume 4. So this is the same growing matrix or lattice of concentric layers of balls in a cube-octahedral conformation, but with rhombic dodecahedra around each ball. So here's without the rhombic dodecahedron, and here's with the rhombic dodecahedron. So this way of teaching the CCP, Arthur Loeb, professor at Harvard, MIT, who taught crystallography, he collaborated with Fuller, and he could see teaching the CCP in terms of concentric layers around a nuclear ball like this. It's not the typical textbook treatment, but when he did it to an audience of other crystallographers, there was pleasure in that. They liked it, in other words, is what this slide is about. You can gain acceptance for this in your normal everyday school if you present it, partly just because it's historically valid. It's what happened, right? Fuller lived and made this contribution, and there's people around the world who already use this math as something to share with their kids, right? I would say, I'm biased, but any serious high school is going to have this information. Otherwise, it's kind of more closer to just frivolity. What you're doing there in that school is kind of daycare, but not taking you seriously as an adult or going to be an adult. My view of high school is that you should go every 15 years or so, because things change, including at the basic level. And now the situation is we have a lot of geriatrics, a lot of dinosaurs trying to run the world who don't even have a high school education, from my point of view, because they didn't go back and take it again. They're like people who learned to drive a long time ago, and they're still out there driving in that old way and trying to run the world, or think they are, right? I'm talking about these politicians, the ones who drum up all this fear in us. And it's because they don't know how to drive, right? They're completely clueless by this point. Not interesting what they think to me. So, except they can destroy a lot of people with what they think. So, yeah, that part's interesting. So, yeah, we have a different coordinate system for our IVM if we like. We can use what are called quadrays, and I have a whole other slide deck on these quadrays, which use what's called a caltrop as their core frame, this thing. 4 unit vectors, except they're not unit vectors. They're a different length than 1. So in XYZ, we have plus minus X, plus minus Y, plus minus Z. Here we just have 4, we use the 4 positive spokes, and they go to the corners of tetrahedron, and its edges are a unit. So this makes a tetrahedron of edges. Those are the ones that are units. So these 4 spokes even though I can call them basis vectors, I will not call them unit vectors necessarily. So those caltrop versus the jack, they're both used in kind of malicious ways to pop tires and stuff. Okay, so but also as ocean break, water break, things to keep the ocean from tsunamiing into your town. Like Crescent City, California has a monument to the caltrop. They call it a tetrapod because they have big piles of them underwater to hopefully present a breakwater, because they did have a tsunami in the 60s and are trying to forestall that happening again. Again, a lot of low hanging fruit when you move away from 90 degrees as your orthodoxy and start using more 60 degrees. You'll find interesting things. For example, on the right, we make a big deal of this in other contexts. If you just pick 4 balls at random in the CCP and connect them with 6 edges, you'll get a whole number tetravolume, or 0, but that's also a whole number, right? So quadrate coordinates, this is from Wikipedia. I'm going to update this slide because it was pointed out to me that I don't bother to show EFGH in the diagram, and it should be explained that that's so there's not too much clutter. There's so many letters there already. But basically, once you have those 4 vectors to the corners of a tetrahedron, you can add them in simple ways, typical vector addition, the way we normally do, to get 26 overall vertices that comprise what we call the concentric hierarchy. So you can see those summations, vertex inventory as sums of quadrates on the chart, and then you'll see the corresponding ones, except EFGH are missing on the right side where I'm showing you what points I'm talking about. We pick up 2 tetrahedra, the cube, the octahedron, rhombic dodecahedron, and cube-octahedron, 26 points. So with that established, all of that, we go back to the literature and we come into regular polytopes, where Donald Coxeter, the author, is saying you shouldn't confuse in your mind these 2 different meanings, 2 different namespaces, using 4th dimension or 4-dimensional. There's the one with the tesseract and the pentatope if it's a tetrahedron, and then 6D, 4D, 5D, 6D, as many dimensions as you want. They're all like spatial dimensions, and we call this extended Euclidean geometry. That is different from Einstein's use of the 4th dimension for time. Mathematically, it looks different. 3D plus time does not go to paper in the same math, the same algebra as what Coxeter is doing as an Euclidean geometer, University of Toronto. And Fuller dedicates synergetics to him, saying, basically he knows this stuff's going to be important, always going to be important, like what Coxeter's up to and this whole namespace he's working in. Hilbert space isn't going away. XYZ isn't going away. It's an accomplishment of our culture that is not, it's not bogus. It works. And then synergetics comes along. It also works. It does not have to shove aside and replace. It merely is another namespace that works side by side. Now, it can help us, though, with our intuitions and help us understand how triangles are stronger than squares structurally. The biases that synergetics introduces to the culture, those will revector our thinking. Our culture will change, but not because we're on the warpath to purge Hilbert space and Coxeter type thinking. Fuller dedicated synergetics to this Euclidean geometer. Makes sense to remember that and not to get in the mood to attack the cube people. So that's the 4 4D in three different namespaces. Because I'm saying Fuller comes along with his 4D and it's yet different again. It's not the Coxeter way of doing fourth dimension. It's not the Einstein way of doing fourth dimension. It's Fuller's way of doing fourth dimension, which is to say a tetrahedron is where it all begins in terms of spatial awareness, having volume at all to begin with, the sort of Kantian idea, the very basic primitive feel of res extensa is going to be 4 walls. You can't have fewer walls in a room. 6 walls of a cube, that's overdoing it. You've got 6 square walls, you didn't need that. 4 triangles. And that creates a container. And so we start from there. It's a different logic, and we build volume around it consistently as well. And this happened. This was a great futurist of the 1900s, and it's a very elementary innovation with a lot of low-hanging fruits, very interesting stuff. And yet the secondary literature hasn't been a lot of it because we have a lot of cowards out there. A lot of people who would just as soon shove all this under the rug. Partly because Fuller had political views that they don't like. So it's not because the math is wrong, it's because the politics are wrong, right? A lot of suppression of the Fuller syllabus because of cowardice, very clearly. That's why I say if you go to a school that has any amount of backbone, any amount of spine, then this stuff's, you've already had this, you know this already. If you don't know this, wow, did you get ripped off? I hope you're not paying student debt. Because if you went to college and they didn't tell you any of this, oh God, you poor slobs. I feel bad for you. Anyway, we go on with the Tetra book and how to, there's a lot of pedagogical techniques that most teachers who know anything are using already to understand about how to go back and forth between the 2 volume systems, XYZ and IVM. I alluded a bit to synergetics constant. So we cover that stuff and show how, it goes way back in Fuller's thinking, second root of 9/8, stuff like that, and how he thinks in terms of revectoring certain, size versus shape and so on. You'll find physics guys into this too. By guys, I mean any gender. It's like there's been a lot of sort of precessional osmotic effects in the culture already, thanks to synergetics. But a lot of people don't know to trace it back to this source because they're not given that information. Darcy Thompson questioning, why do we say 3D instead of 4D? So he's on that same line of inquiry as Fuller was back in 1918, this letter. And Fuller doesn't really publish synergetics until 1975. So this has been, but he starts work on it more or less big time in 1928, 27, 28, and going forward, right? So I'm just saying the Fuller syllabus is part of the zeitgeist. And once you crack it open and start reading what's been going on, you can connect to Carl Menger, geometry of lumps. The kind of thinking Fuller was doing was not as offbeat as some people would like you to believe. It's actually already made a big difference in terms of helping us integrate what the 1900s was all about in terms of the themes that they tackled, such as sphere packing, such as space-filling tetrahedra. And this is why Escher's work is so topical. When you read synergetics, you think, wow, these two ought to go together. And that was a plan, actually, that Arthur Loeb I mentioned was hoping to get those two more directly working together. But Escher passed away. So that's about it. this is the history that you're going to want to make sure you know. Art book by Linda Dalrymple Henderson called The Fourth Dimension in Non-Euclidean Geometry in Modern Art. Highly recommended if you're into art at all, to understand the role again of the 4D meme and how it's split and forked. And then I do this joke about how quixotic is synergetics, I ask. And I'm basically saying, hey, we're the establishment now. This is the deep state. You know, we're the ones in charge here. So we're the windmills, right? We are the windmills. Like, if you don't know synergetics at all, you're really pretty much out of the loop as to what's going on in the world. That would be my polemics, right? I'm purposely trying to, like, stir the pot here, get people riled up a bit, right? It's like if you went to school and no one taught you any of this and you're paying debt, you're paying student debt, and this was it withheld from you from high school forward. Wow, you got ripped off big time. And now they want you to pay them. That's pretty funny, isn't it? I laugh. I'm not laughing at you. I'm just saying the whole system is really corrupt and ugly to contemplate. But this stuff's pretty. This is aesthetically beautiful. And so I like to hang out here and I like to give these slideshows, and I'm inviting you to join me. Like, get out of the mud and give us something worthwhile as part of literature or math, take your pick. Be that teacher you want to be. Don't just take all the garbage that you're inheriting and try to recycle the garbage. Go for this new novel material as well. I'm not saying throw out everything else. I'm just saying you got to include this if you want to be taken seriously, especially if you're in politics. If you're out there, if you're like in the Senate or something and you don't know what I just showed, go to high school. Get a degree in high school again. It's not too late. All right. I hope that was fun. We'll talk again.